Until now, we have, for the last few classes, been largely dealing with some of the mathematical requisites and the basic formulation of the problem. Now let us move on to a few examples and then come back to the mathematical aspects of the problem of quantum mechanics again. So let us go on to some particular problems. We are now more or less equipped to deal with some simple problems in quantum mechanics. So the problem we shall be starting with right now is the motion of a particle in one dimension in a potential. So in a motion of a particle in a one-dimensional potential well. So one-dimensional potential. So we shall consider some simple examples of particles moving in a one-dimensional potential. So for such a particle, this is one dimension here, x. We shall be referring to it as x. And there is a particle free to move along this. And there is a potential. We have already considered a particle without any potential, free to move in one direction. So the new thing is the potential. We also know that corresponding to every dynamical quantity which we have in classical mechanics, there are operators. So for the position of a particle, there is an operator x, whose action on wave function we have already discussed. We also have the momentum operator p, which is, this is the x component of the momentum, which is minus I h cross del by del x. So whose action on the wave function is also well known. Let me also introduce one more quantity which arises in classical mechanics called the Hamiltonian. This is something which most of you may not be familiar with as yet. So we have another quantity in classical mechanics called the Hamiltonian, which is usually denoted by h. And in classical mechanics, the Hamiltonian is a function of the momentum and the position. So for a particle moving in one dimension, the Hamiltonian is a function of the position and the momentum, and it is equal to p square by 2m plus v. For a potential which is independent of time, this is the Hamiltonian. For systems which are time independent, for systems where the potential does not depend on time, the Hamiltonian also corresponds to the energy of the system. So if the potential is time independent, the Hamiltonian corresponds to the energy of the system, which you can see here. It is the kinetic energy plus the potential energy. We shall discuss more about the Hamiltonian later on, and those of you who are doing a course on classical mechanics right now will be encountering the Hamiltonian as you proceed along the course in classical mechanics. Right now we are dealing only with systems which are time independent, and for time independent systems the Hamiltonian corresponds to the energy of the particle, or energy of the system. So the Hamiltonian in quantum mechanics is an operator which is a function of the momentum and position operators. So we can make everything into operators, and we have this. So the Hamiltonian for a time independent system is the operator corresponding to the energy. Now if you go back to your Schrödinger equation, you will see that the Schrödinger equation can be now written in terms of the Hamiltonian as I h cross del by del t psi x and t is equal to h psi. Where h, if we plug in the form of H, then this is P square. P square is minus I H cross del by del x square by 2m psi, this is P square acting on psi, plus V x acting on psi, which is the same old Schrodinger equation. In one dimension, the gradient, the nabla is replaced by del x, or we have minus h cross square by 2m del by del x square psi plus v psi. So we see that this is equivalent to the Schrodinger equation. So this is the most general form of the Schrodinger equation. If you know the Hamiltonian for a system, you can write down the Schrodinger equation. And the Hamiltonian is the operator corresponding to the energy. So for a time independent system, if you make a measurement of the energy, this corresponds to the action of the Hamiltonian operator. The energy for a time independent system is represented in quantum mechanics by the Hamiltonian operator. Now let us look at solutions of this Schrodinger equation in a situation where V is a function of x alone. It is a time independent potential. In such a situation, we can proceed by the method of separation of variables. So psi, which in general is a function of x and t, can be written as the product of one function of time and some other function of position alone. Let us use the same symbol psi for the function of position alone. To differentiate between this function and this function, all you have to do is note that there is x and t explicitly here and there is no t here. To make this difference more explicit, let me also put a bar at the bottom. But we shall be using psi for both the time dependent wave function as well as the wave function depending on the position alone. So we shall use this as a trial solution for the Schrodinger equation and see if we can get a solution. So the Schrodinger equation with this trial solution now becomes the time derivative will act only on this function of time, and we can take this psi x outside. So we have I h cross psi, let me write it here clearly, I h cross psi of x del by del t of this function of time is equal to minus h cross square by 2m. Here we have a derivative with respect to x which will not act on this function of time, so I can take it out, t, and then I have del by del square of psi of x plus v of x into t into psi. And if we divide this equation by psi into t, then we get the following. We get I h cross, we divide it by psi into t, so we have 1 by t here, the psi gets cancelled out, so we have del by del t of this capital T here is equal to minus h cross square by 2m 1 by psi del square del x square psi plus v x. So this equation, if I divide it by the capital T into psi, gets reduced to this equation, because this psi gets cancelled out when I divide it by psi into t. I have a 1 by t left here. This t gets cancelled out, I have a 1 by psi left here, and both t and psi get cancelled out from the third term. So we have this equation. Now if you look at this equation carefully, you will notice that the terms on the left hand side do not have any x dependence, and the terms on the right hand side do not have any t dependence. So we have something which is a function of t is equal to something which is just a function of x. So if I change t here, this value will change, but this will not change. Whereas if I keep t fixed and change x, then this will remain fixed, this will not change. So this implies that this whole thing must be equal to a constant which I will call E. And the reason for calling this constant E will become clear just now. So we now have two different equations. Let me write down these two different equations separately here. So the first equation that we have is I h cross del by del t is equal to E into capital T. The second equation which we have is minus h cross square by 2m del by del x square psi plus v psi is equal to E psi, where psi is a function of x alone, let me put it here, and t is a function of time alone. This equation can also be written as h psi is equal to E psi, because this is nothing but the h, the Hamiltonian operator. This is the momentum squared, this is the potential. So this is nothing but the Hamiltonian operator acting on the wave function. So this equation is nothing but the Hamiltonian acting on the wave function, giving us E into the wave function. So what have we done? We had a partial differential equation. We have reduced it to a set of two ordinary differential equations. These are no longer partial derivatives. These should be ordinary derivatives, because this is just a function of time and I'm differentiating with time. This should be also ordinary derivative with respect to x, because this is just a function of x and I'm differentiating with respect to x. So I have two ordinary differential equations, and there is one unknown constant E which we have obtained in this process. Now what is E? E is the eigenvalue of the Hamiltonian, because the Hamiltonian operator acting on this wave function psi gives us a number E into psi itself. So E is the eigenvalue of the Hamiltonian operator, or you may say that E corresponds to the allowed values of energy. So in some situations these two equations can be solved for any value of E. In some situations I will find that there are only a set of allowed values of E for which I can get solutions for this equation. Whatever it is, the values of E which are permitted are the allowed values of energy for that system. Because if I make a measurement of the energy of the system, I will get one of the eigenvalues of the Hamiltonian operator which corresponds to the energy. So the allowed values of energy are the allowed eigenvalues E. And these are the eigenfunctions, energy eigenfunctions. So I can label them as psi E. So this is the particular eigenfunction corresponding to the eigenvalue E, and E can take different values. Okay, so let us now go ahead and solve these two equations. The first equation is very simple to solve. The first equation, the solution of the first equation is just this. The time part is just e to the power minus I E into t by h cross, something which is already familiar. You must have encountered this earlier when we considered the free particle. So for a free particle, we found that the time evolution for a particle with energy E was described by, the time part of the evolution was described by this, an exponential which keeps on oscillating with frequency omega, which is E by h cross. So the time evolution is this. So if I have a wave function corresponding to an energy E, then the time part of that wave function is just this exponential of the imaginary number, which is just an oscillating part, and the frequency of oscillation is E by h cross. Or if you think of this as a phase, the phase keeps on going. The h cross is in the denominator. There is a line here dividing the two. Is it clear, or should I write it again? Okay. So this is the time dependence of this wave function. Now, if you want to solve the spatial dependence of the wave function, then you have to actually solve this equation, which we have already solved for a free particle. We found that they correspond to plane waves e to the power I px. For situations with a potential, the solution is not so simple, and we shall be discussing a few cases as we go along. So this is what we shall be focusing on. Now, so let me recapitulate what we have got. So we have obtained solution so the full time dependent Schrodinger equation has got solutions corresponding to some fixed values of energy. So these are all solutions which are different energy eigenvalues, or they are eigenfunctions of the Hamiltonian operator, and this has got a very simple time dependence, which is e to the power minus I e into t by h cross into some function of x. So this is a general form of the solutions of the time independent Schrodinger equation. The time dependence has been solved, and now we are left with a time independent equation, which is this equation here, which is also this equation here, which gives us the solutions of which will give us the eigenfunctions of the Hamiltonian operator. And in many elementary applications of quantum mechanics, in many elementary courses where only time independent situations are dealt with, this is often called the Schrodinger equation. This equation or this equation is often referred to as the Schrodinger equation instead of the time dependent partial differential equation. So in a situation where the potential does not depend on time, the whole problem reduces to solving this equation. Once you can solve this equation, you can find out the eigenfunctions of the energy, you can get the eigenvalues, the allowed eigenvalues of the energy. Once you have this, the whole system is solved. These states are called stationary states of the system. Why are these states called the stationary states of the system? The reason is very simple. These states, the time dependence of these states is only through this phase. So the wave function, the eigenfunctions of the Hamiltonian operator, this gets multiplied with a time dependent phase. This is just a phase, nothing else. It is cos of something plus I sine of something. It is just a phase. So the time evolution is just through this phase, nothing else. This does not affect expectation values or any physical quantities which you might want to measure. So if a system is in one of these states, it does not in any way affect any of the expectation values which you may want to measure. You can easily check that, for example, the expectation value of the position is given by the mod square of is given by this quantity. When I take the mod of this wave function, this does not contribute. So the mod of this is equal to just the mod of this part, and this is equal to, I can put this here, just the mod of just this much. So this is just equal to so for a stationary state, the expectation value of say position does not change in time. Although the wave function itself changes in time, the change in time, the time evolution is just through a phase, multiplication through a different phase. And this in no way affects expectation values, because when I take the complex conjugate and multiply it with itself, this does not contribute. And expectation values are time independent for such states. And these are called stationary states of the system. If I have a system in such a state and I evolve it in time, it remains in the same eigen state of the energy. So suppose I have a system, I measure the energy, I find that it has a certain value E. I let it evolve in time. So once I know that it has got a value E, I know the wave function at the time of measurement. As it evolves in time, it just this phase keeps on changing. If I make a measurement of energy later on, it still remains in the same eigen function of energy, and I will get the same energy again. So it will just remain in that state. So that is why these are called stationary states. And the expectation value of say position, momentum or any such quantity does not change for such states. If I have a superposition of two different states, that is not an stationary state. Each of these individually is a stationary state, but a superposition of two different such states is not a stationary state, because if I superpose two different such states, let us say I take C1 psi E1 plus C2 psi E2, then this will be equal to C1 e to the power minus I E1 into T by H cross into psi Ex plus C2 into e to the power minus I E2 into T by H cross psi 2x psi E1 and psi E2. Now you see that the relative phases here and here, this oscillates at a particular frequency, this oscillates at a different frequency. And depending on the time instant when I am adding these two, they may add up constructively or destructively, and this will no longer be a stationary state. So now this evolves in time. Whereas if I have just one of these, this does not evolve in time. So these are called stationary states, but if I superpose two of them or many of them, the resulting state will no longer be stationary. So whenever we are encountered with a quantum system, a particular quantum mechanical problem, the first question we ask is, what are the stationary states of this system? Once I have solved the stationary states, I know that if I make a measurement of say position of energy, I know what are the allowed values. In addition, I know the time evolution of each of these states. So I also know the time evolution of each of these wave functions. Now suppose the system is not in a stationary state, it is in some arbitrary state. I have already told you that these eigenfunctions form a complete basis. So the eigenfunctions of energy also form a complete basis. And I can express any arbitrary wave function in terms of these eigenfunctions of energy, and I know the time evolution of each of these eigenfunctions of energy, so I can use this to find out the time evolution of any arbitrary wave function. This is what I have asked you to do in the assignment of the Gaussian wave packet, where we have a free particle. The free particle is in some arbitrary wave function, not arbitrary, is in a Gaussian wave packet state. That I can express as a superposition of stationary states. What are the stationary states for a free particle? The stationary states for a free particle are just these: e to the power I by h cross px minus et. So this is a particular stationary state of a free particle. Now the energy here does not uniquely define the state, because I can have plus p and minus p corresponding to the same energy. So I have to use the momentum to actually label these wave functions. But for every value of momentum I have a different wave function, and these are the stationary states of the free particle without a potential. So if I make a measurement of momentum and I have a system in some arbitrary, so this is p, psi p. If I have a system in some arbitrary state psi and I make a measurement of momentum, it will give me one of these with some value of p, and that will be the value of momentum which I get. So any arbitrary psi I can express as a superposition of these, and I know how each of these evolves, so I can find out how this evolves in time. And this is what I have asked you to do for the Gaussian wave packet. So hopefully as we go along, these things will make more and more sense to you. Now let us go on to a situation where we have a potential. So we shall be looking at the thing which we usually study in classical mechanics after we have understood a free particle, that is a simple harmonic oscillator. So we shall be studying a simple harmonic oscillator in quantum mechanics. So let us move on to a simple harmonic oscillator. So the simple harmonic oscillator has a potential energy V which depends on x, and this is equal to half k x squared. So I can draw the potential energy here. It is symmetric around x equal to 0 and it is a parabola. So this is how the potential looks like for a simple harmonic oscillator. And we know classically that if I have a particle moving in such a potential well, then its motion is a oscillation with angular frequency omega, which is equal to square root of k by the mass of the particle. So these are familiar results which we should have done when we were in school. So just refresh yourselves with this if you have forgotten. So if I have a particle here, it will oscillate with this angular frequency. Now the simple harmonic oscillator is extremely important in all of physics for various reasons. One of the reasons why it is very important is as follows. Suppose I have some situation which is in equilibrium, and I want to study what happens if I disturb it slightly from this equilibrium. So for example, I have many atoms in a solid, and there is some equilibrium configuration of these atoms where they don't move. The total forces acting on them is balanced, and if I have a small disturbance, it will tend to move it back. So in such a situation, if x not be the equilibrium point, let us look at a particle which is in equilibrium. So the potential for a small disturbance around x naught, we can do a Taylor expansion. So this will be V x naught plus x minus x naught into the first derivative, which I denote by this dash, plus half x minus x naught square V double dash. This is at x equal to x naught. This is also at x equal to x naught. Okay. So we have done a Taylor expansion of this potential around x naught. So we have a particle which, when it is at x naught, it is at equilibrium, and we want to study what happens if I disturb it slightly from equilibrium. So in order to do that, we can look at the potential around the equilibrium point x naught, and for small disturbances we can just do a Taylor expansion, and this is the form of the potential. The fact that the particle is at equilibrium at x naught tells us that the first derivative of v, which is the force, should be 0. So for equilibrium, this term will vanish. And the lowest correction which we have is just something which is quadratic in the displacement, which is the simple harmonic oscillator potential. So if you want to study small disturbances around some equilibrium point, then the potential is quadratic around the equilibrium point. So if you want to study vibrations of atoms in a solid, for example, if you disturb them slightly from the equilibrium point, you can approximate the vibration as if the particle were moving in some simple harmonic potential for small vibrations. If the vibration is large, this approximation breaks down. But for small disturbances around the equilibrium, the potential is quadratic. This is one reason why the simple harmonic oscillator is so very important in physics. In most situations where you are studying small disturbances from equilibrium, it is a quadratic potential. In addition, there are various fields like electromagnetic field, or even sound waves where each individual mode of the oscillation, so electromagnetic field is a field defined everywhere, you can decompose this into different modes, and each individual mode of the electromagnetic wave actually behaves, the mathematical equation is that of a simple harmonic oscillator. So that is another reason why the study of the simple harmonic oscillator is very important if you are going to quantize fields, which is not that something which we shall be doing here, but if you want to really quantize fields, then you will encounter simple harmonic oscillators. So with this brief motivation, let me go on to the analysis of the simple harmonic oscillator problem. So the time evolution of the wave function is done because the potential does not depend on time, and we can easily solve the time evolution. So we have to now look at this equation for the simple harmonic oscillator problem. Minus h cross square by 2m d by d x square psi x, this plus half k x square psi is equal to E psi. So psi is a function of x alone. This is p square acting on psi plus the potential half kx square acting on psi is equal to the energy into psi. So we have to solve this for different values of energy. So this okay, so this is the problem we have at hand. We want to obtain solutions of this equation. Now it is convenient to proceed by introducing some dimensionless variable instead of x. So how do we go about doing this? Well, first of all, we replace k by omega. So this is omega square into m. K is omega square into m. In addition, let us do a small dimensional analysis. We know that h cross has got dimensions energy into time. So this will be m L T L by T square into T. This is h cross. The other quantities which we have in this equation are m, which is the mass, and we have omega which is 1 by T. So if we want to make something of, so we have the mass, in addition we have the mass of the particle, which is m, we have omega, which is 1 by t. So if you want to make something of dimension of length, then the quantity which you have to, so you have to make a combination of these three and get a dimension of something of dimension of length. So how do we go about doing that? So let us see. So we have to take h cross, and then we have to take omega, m omega by h cross, h cross by m omega. So h cross by m omega will give us something which is L square. So the square root of this will give us something which is just position, and this is, let us call it x naught, some typical length scale which appears in this problem. So in this problem there is one length scale x naught which appears. So if we scale, so if we define x by x naught to be equal to xi, some dimensionless length number which characterizes the length, then we can simplify this equation and make it totally dimensionless. So let us do that. If we do that, let us see what we get. So, or okay, let me write down what it gives you if you do such a simplification. So what you get if you do such a simplification is as follows. You have minus d square d xi square. Now psi is a function of xi, and then you have plus xi square psi. Let me keep this here so that you can compare the two, is equal to 2e by h cross omega xi. So by multiplying throughout this equation by suitable factors of h cross m and omega, we can write the whole thing in terms of xi, and what we get, and then we multiply by 2, etc., and the resulting equation is this. Which you can further simplify. So let me write that also here, okay, which we can simplify to the following: d square d xi square psi plus 2e by, or let us replace this by n, some number n. Sorry, this is psi, not xi. Psi. And then we have n, 2, let us call this 2n here, 2n psi minus xi square psi is equal to 0, where 2n is equal to 2e by h cross omega. Okay. So this is the equation we shall be dealing with. Now, okay. Now let us choose a trial form of the solution psi, which is some function of xi, let us call it v xi, into e to the power minus xi square by 2. So we will express this solution psi which we are looking for in terms of some function v of xi into a Gaussian e to the power minus xi square by 2. So let us now work out the derivatives of this function in terms of the derivatives of this and this. So let us work out these derivatives and then plug them into the Schrodinger equation. So we have psi dash, let us use dash to indicate the first derivative. This is equal to, we have one term which is v dash into e to the power minus xi square by 2, and we have one more term which is minus v into xi into e to the power minus xi square by 2. Let us also calculate the second derivative, which will give us one term which is v double prime e to the power minus xi square by 2, and then we will have one term where we differentiate this once and where we differentiate this once. So this will give us minus 2 v prime into xi into e to the power minus xi square by 2. One of these arises from here when you differentiate this. The other one arises when you differentiate this. So we get minus 2 here. And then we have one term when I differentiate the xi over here, which gives us minus v into e to the power minus xi square by 2. And then I have another term which is plus v xi square e to the power minus xi square by 2. This is when I differentiate this. So the second derivative of psi has all these 4 terms. Now if I use this in this equation, so I have to just replace the second derivative of psi in this equation, we find that this term is, let us see, is, have we made a mistake in sign? Let us see here. So this should, so I move this here and then, okay. So let us proceed now. So this okay, this term here and this term here are exactly same and equal and with opposite sign, so they exactly cancel out, because v into e to the power minus xi square by 2 is psi. So this term is xi square into psi. This is also xi square into psi. So when I replace this here, this term will exactly cancel out this term here. So putting this all together, let us see what we are left with. So what we are left with, when I replace the second derivative of psi, then I have v double dot. Now if I put this in this equation, then this e to the power minus xi square by 2 cancels out from everywhere, so I'm not writing it anymore. And what we are left with is an equation for v. So let me just put down this equation. What we are left with is v double prime minus 2 v prime xi plus, or rather minus v. This is what arises from psi double prime. This is what arises from psi double prime. I already told you that this will cancel out with one of the terms which was there in the Schrodinger equation. So this, and then we have plus 2n v is equal to 0. Or we are left with this equation v double prime minus 2 xi V prime plus 2n minus 1 V is equal to 0. So this is the differential equation which the function V has to satisfy. Now let us just, so we see that it is more convenient if we define this to be something instead of, so it is more convenient if we define, instead of choosing 2n to be E by 2E by h cross omega, it is more convenient if we define 2n minus 1 to be 2E by h cross omega. So I am just changing the definition of n. Okay, so n, we are 2n, I am defining to be equal to 2E by h cross omega, or rather, okay, no, sorry, let me not create unnecessary confusion. Let me just use some other notation. We shall go back and change it later on. So let us call this 2n tilde. Okay. So this equation then reduces to V double prime minus 2 xi V prime plus 2n tilde V is equal to 0. Now we have to solve this equation. So we proceed by doing a series solution. So we represent V of xi as some series like this, with m going from 0 to infinity, Cm xi m. So what do we get when we use this? Let us calculate what V, so this term is just this whole thing into 2n. So let us, okay, what is V prime? V prime is now equal to summation over m going from 1 to infinity, Cm into m into xi m minus 1, or xi into V prime is equal to m equal to 0 to infinity Cm into m into xi m. So when m is 0, it gives us 0, and when m is 1, 2, 3, 4, it gives us the corresponding value. Let us also calculate V double prime. So this will be equal to m equal to 2 to infinity Cm into m into m minus 1 into xi m minus 2. So we have these relations for V, V prime and V double prime. Now we have to use these in this equation and then obtain a relation between the different Cm's, the different coefficients of this expansion. Okay, so I shall be doing that in the next class. I shall stop here for today.